Welcome to springlib.
We want to describe how the graph of f of x is equal to e to the x plus c times e to the negative x varies as c varies. Then we want to graph several members of this family to illustrate the trends that we discover. And in particular, we want to investigate how the maximum, minimum, and points of inflection move when c changes. We also should identify any kind of transitional values where the basic shape of the curve changes also. So first, let's just go ahead and maybe find what our x-intercepts should be. That might be something nice to know. So to do that, we can go ahead and set this equal to 0. But before we do that, I'm going to factor out e to the negative x. I get e to the negative x. So it's going to be e to the 2x plus c. Now, if we set this here equal to 0, well, we know e to the negative x can never be 0 since e to the negative x is always positive. So that's going to tell us e to the negative 2x has to be negative c. Take the natural log of each side. And that'll give us 2x is equal to the natural log of negative c, and then divide each side by 2, and we get x is equal to 1/2 natural log of negative c. Now, something you might notice is that this will only be defined when c is strictly less than 0, since we can't take the natural log of 0, nor can we take the natural log of a negative number. So we'll only have x-intercepts when c is strictly less than 0, it looks like. All right. Now, if this here is f of x, let's go ahead and find our first derivative, so we can possibly find our maxes and mins. Well, the derivative of e to the x is just e to the x, and the derivative of e to the negative x is just negative e to the negative x, so it'll be minus c e to the negative x. So once again, let's factor out that e to the negative x. So e to the negative x is equal to e to the 2x minus c. And again, we're going to set this here equal to 0. E to the negative x can't be 0, so the other part has to be 0. So e to the 2x is equal to c, natural log of each side. So that will give us 2x is equal to the natural log of c, divided by 2. We get x is equal to 1/2 natural log of c. And now we will only have where this is a maximum or a minimum when x is strictly, or not x, but c is strictly larger than 0 for the same rationale as before. We can't take the natural log of something that's 0, nor can we take the natural log of something that is negative. All right, and let's just see real quick if this will be a maximum or a minimum value. Or actually, we can see that when we actually start to graph. All right, so then for the second derivative, we'll taking the second derivative of this will be e to the x. And then again, we'll just change the sign, so it'll be plus c e to the negative x. So if we set this here equal to 0, well, this is the same thing as f of x. So we already know right away that x is going to be 1/2 natural log of negative c. So c has to be strictly less than, but this only occurs when c is strictly less than 0. So this would be our inflection point if c is less than 0. This will be our maximum or minimum when c is strictly greater than 0, and this will be our x-intercept. All right, so let's go ahead and see if this matches up. Or actually, before we do that, let's do one other thing. So notice if we were to just let c equal to 0, f of x becomes e to the x. And we know the derivative of e to the x is just e to the x. So this here would have no maximums nor minimums, but we might say that around c is equal to 0, this is probably our transition that they were saying we should look for, just because e to the x will have different properties than when we're adding e to the negative x to it. All right, so I went ahead and graphed a couple of these here. And let's just go ahead and write what our max and min should be. So remember our max or min, and in this case we can see that it should be minimums because we said that we only got a minimum or a max when c was strictly larger than 0. Remember that was going to be at x is equal to the natural log of 1/2 c. And we know our point of inflection was only when c was strictly less than 0, and that was x is equal to 1/2 natural log of negative c. All right. And remember, this was also the same as our x-intercept. So at c is equal to 0, we see we just get the function e to the x. And then when we start to go towards the positive values, we see that, so for c is equal to 1, well, natural log of 1 is 0. So then our minimum would just be at x is equal to 0. And then as x increases, so does where the x value will be. So it shifts to the right for the maximum, or for the minimum of this. And we're not going to have any inflection points for when c is bigger than 0, but we can come to the other side to see our inflection point change. So again, when c is equal to -1, we'd get natural log of 0, or natural log of 1, which would just be 0. So at x is equal to 0, we have this point of inflection. So to the left of it, it looks concave down, and to the right is concave up. And similarly, when c is equal to -5, well, wherever our intercept is, that is where the function has this point of inflection. So I would say this describes all the relevant information for this class of functions.